All right, so optimization, and like I said before I hit record, I'm going to be looking for global maximums for maximizing, and I'm going to be looking for global minimums when I'm trying to minimize things like cost or minimize like amount of fence that you have to use to enclose a certain area, just things like that. You know how they like to write these word problems. But yeah, first derivative is a pretty big deal. What I was trying to get at before I hit the record button was watch your restricted domains. You know IB likes to play with those things. Okay, just watch out for them. So we just jump right into it. There's not even like notes to talk about. You just jump right into it and you use the first derivatives to look for sign changes. A rectangular cake dish, and what we're talking about is a pan, a cake pan. Okay. So I guess a rectangular cake pan is made by cutting out squares from the corners of a rectangle of tin plate, and we have the dimensions. Then folding the metal, so fold the sides up to form a container, an open top box. What we want to know is what size of the squares must be cut out to produce the cake dish that has the maximum volume. You know what would really help? Picture! Picture time. You know what? I'm not dumb. I'm going to draw it in pencil in case I goof it up. So here is our piece of tin or aluminum, whatever your pan is made out of, that we're going to be cutting. Picture not drawn to scale, obviously. Now what we're going to do is we're going to have a machine come by that stamps out squares. Doing my best here. So the regions that are outlined in red dotted line will be gone. So this for what should have been squares will be gone. And what you'll end up doing is the machine of some sort, because I doubt humans are doing it, is going to fold along this line, this line, this line, and this line to create an open top pan. Okay, behold the geometry skills. It's my pan. Ta-da! I was a geometry teacher for years. What's that? So it's rectangle, and then this is a parallelogram. Then you just make, and then you have a parallelogram as the top. So it's a rectangle with a fat parallelogram, skinny parallelogram, and then just straight down. And this should have been a little bit of a better angle like that, and that you try to make parallel to that. Okay, so anyway, there's our cake pan. Now what we need to do is we need to put some dimensions on this bad boy. Yeah? Okay. Well, originally, before we cut out these red rectangles, which should have been squares, what we had was a piece of pan that was 40 centimeters, 40 centimeters, units are not that important, 40 wide, and 25 high. And then we folded it up, right, to create this. So clearly, this thing is not going to be 40 by 25. Now, unfortunately, the way I drew it, mine seems to be longer this way than this way. So this longer edge on my picture ended up being over here. I'm sorry. My original was better. Anyway, this side went over here. But what we did was we cut an unknown sized square out of the side. So what we want to do is we want to call that square an x by x square. So originally this side had a length of 40. And then I punched out these two squares. So how much metal is left?
40 minus 2x.
40 minus 2x. So right here on the box, because the way I drew it, is a 40 minus 2x. And by that same logic, this was 25. A couple squares were punched out of it. Again, the way I drew it, leaving right here 25 minus 2x. But we're talking about volume. Volume requires a third dimension. We need to know how deep this cake pan is. It's x. This edge is found by putting that edge and that edge together. That's what creates it. Okay, so it is x tall. Great. Now that we have the length, width, and height of our cake pan, we can write a volume equation for that. Volume is, well, volume with respect to x, my apologies, is. What's length, width, and height, right? And multiplication doesn't care about order. So I'm going to put the x on the front, and then I have 25 minus 2x times 40 minus 2x. This is my volume equation. Since this is a senior level IB class, I'm going to assume everybody in the room knows how to FOIL. Okay, so when you FOIL these two guys together, you still have that x on the outside, giving you 4x squared. Of course, I've also written it in standard form, minus 130x plus 1,000. And then lastly, distribute your x. Cool. Some kind of positive cubic function. You don't need to draw this, but just so you keep it in mind, we've got something like this going on. We're trying to maximize our area. Volume. Clearly that's going to happen here-ish. So I'm assuming we're got a curve like this of some sort. Now, Mr. M, how could we possibly maximize when it's a positive cubic and it's going to grow forever? I go, well, because your squares are limited by how large the piece of metal was before you started cutting. So this function can't go forever. It will have an x that stops being possible. There will be a time when x cannot get any bigger.
12 and a half.
It's going to be 12 and a half. Now, how did you know it was 12 and a half?
25 divided by 2x.
Right. So this was the smaller side, so it was actually the more limiting side. And since we're taking 2x out of it, we know that the maximum that x could actually approach would be half of 25. You basically just set the 25 minus 2x equal to 0 and solve for x. But it can't be 12 and a half because that would eliminate the entire side. So it has to be strictly less than 12 and a half. And what would be the absolute smallest value that x could approach?
0.
0. It can't equal 0 because if it equals 0, you can't fold this thing. So we actually have a restricted domain from 0 to 12 and a half, and I'm assuming that 12 and a half happens somewhere like right here. That looks like 17 and a half, 12 and a half, like that. Again, this wasn't necessary, this was. Because what we're going to do now is, we're going to figure out where this maximum is using the first derivative. And it had better lie between these two x values. Let's find our first derivative. Let's use purple. V prime. Bring the 3 down, get 12x squared. Bring the 2 down, minus 260x plus 1,000. Oh goodness, guess what? It factors. I know, those are big numbers. It gets a little bit better though because there's a GCF of 4 at least. So you can at least do that. 3x squared minus 65x plus 250. Again, I kind of have to make some assumptions about the ability level in the room. By this point in our high school career, I'm going to have to assume you can factor a quadratic. Because if you couldn't, you could always use a quadratic formula. It would suck, but you could. The two numbers that multiply to 750 that add to negative 65. 3 times 250 is 750.
sorry.
How you got
Hold on, what was the question?
Can you explain why you got 12.5?
12.5? Okay, where did the well, so you know that of my original pan, this is the smaller side, right? So this is the limiting amount of material. I have to cut 2 x's out of it. So at what point in time does 25 minus 2x become 0? At 12 and a half. So you just set the limiting side equal to 0 and solve for x. And that's the number you're not allowed to take. And obviously you have to take something more than 0. Good? So yeah, the two numbers that multiply to 750 that add to negative 65 are negative 50 and negative 15. So using our Lizzie method, we get x minus 15 over and x minus 50 over what? Over a. That's your Lizzie method. So the 4 literally means nothing because it doesn't, oh, sorry, my picture was so crooked. The 4 doesn't mean anything because it doesn't have an x. We have x minus 5, and this number is 16 and 2/3. I'm only writing it as 16 and 2/3, so that way you can see that the critical value that comes from this set of parentheses, positive 16 and 2/3, is outside the domain. So really the only thing that mattered here was the x equaling 5 that this gives us. We draw our sign diagram. It has a beginning, it has an end, and a critical value somewhere in between there is 5. We just test our slopes.
How do we need to test our slopes?
Just in case, we don't want to make any assumptions, and because the sign diagram reinforces the idea that a maximum will be found when we go from increasing to decreasing.
Oh, okay.
In case there's more than one critical value that actually fits in the domain, we want to check the signs because one could be a max and the other could be a min. So, I don't know, pick a number between 0 and 5, like 1. If you plug a 1 in here, you're going to get a negative. You plug a 1 in here, you're going to get a negative. And when you multiply two negatives, you do get a positive. And then you could plug in a number like 6. 6 here gives us a positive. 6 here gives us a negative. That product would be negative. So because this thing goes from increasing slopes to decreasing slopes, because of that, we know that the shape around that point looked like this, which makes 5 a maximum, which forces x equals 5 to be where this dot happened. So the original question said, what size squares must be cut out? 5 centimeters by 5 centimeters. Ta-da! Realize the question could have said, what is the maximum volume of the dish? Instead of saying what size square. So then you'd have to, substitute the 5 back in, and you get 15 times 30 times 5. What was that? Big number. 4,500? No, bigger than that. Yikes. I think it's 22,000. Yes, Danielle.
So in the notes it says endpoints must be checked. So if 12.5 is maximum, it would have shown up as a critical value.
Well, so the reason why I haven't bothered checking the endpoints for this one is because of the fact that I was increasing to the left of 5, which guarantees that 0 is below. And because I was decreasing to the right of 5, it guarantees 12.5 is below as well. Now, if I'd had a secondary critical value and another region where I was increasing, I would be forced to check the endpoint to see if the endpoint was higher than this critical value. So, for example, if it came up again, we wouldn't have known how far up it went, so I would have had to check. But because I was decreasing this way and was clearly increasing from here to here, this had to be higher than both of these values. Is that okay? Okay. What do you guys think about that example?
So I have a question.
Yeah.
You usually use the derivative to see where the maximum is going to be.
Yes.
So like you.
Use the derivative, yeah. So if you're ever trying to maximize or minimize something, you just find the derivative, look for the critical value. and then guarantee it's the one you were looking for, max or min, with the sign diagram. Cool? All right. This one says a 4-liter container must have a square base, vertical sides, and an open top. Sounds like a box to me with a square bottom. Okay. Which means the top is a square as well. There's my open top box. If you want to get real fancy, there. Now I'm looking into it. It was closed before I did that. That was a joke. Okay, anyway. I don't need your pity laughs. I'm married. Okay. What do we know? We know that the volume is 40. That's all we know, except for the fact that it's got a square base. Feels like there's not enough information, doesn't it? There is. But it feels like there's not enough, doesn't it? So what do we do? Well, let's label our picture. All we know is that the base is a square. So I'm thinking a really good value to put down there would be x. And then x because it's a square. Now volume would normally be length times width times height, right? Well, I have the length and the width. They're x. I don't know the height, but you know what I do know? I do know that the volume is 40. This will allow me to find an expression for, not 40, sorry. 4, not 40, sorry. Anyway, this will allow me to find an expression for height in terms of x. My height can be written as 4 divided by x squared. So when it says to find the most economical shape, it says it minimizes the surface area of material needed. Oh my goodness. I guess we're going to have to actually find the surface area of this box, get an equation for the surface area, and then minimize that function. Because minimizing it would use the least amount of material while still keeping a volume of 4 liters. You guys remember how to find surface area? Hey, you can just add up all the sides, right? All the faces. So the question becomes, how many of this face would there be? 4 of them. And since it's open topped, it's going to be 4 of these faces plus the square on the bottom. So our surface area in terms of x will be our base plus our 4 faces. And the area, since we're talking about surface area, we're talking about the area of the base, would be x squared, x times x. And the area of the 4 faces would be x times 4 over x squared. Sorry? Yep, thank you. I forgot to write the 4. Thank you. I even wrote the 4 there so I wouldn't forget, but I still forgot. So that gives us x squared plus this 4 times 4 is 16. But there were 2 x's on bottom and 1 on top, so it'll reduce down to a single x on the bottom. So there's our surface area formula. We need to find the derivative of that so we can minimize it. Oh, well, derivatives are a lot easier to find if they're not written like this. So I say we change it to say x squared plus 16x to the negative 1. Now let's find that derivative.
Or I have a question.
Yes, Courtney.
I don't know if this is like very stupid, but where did the x come from by the 4x?
The x by the 4x. Oh, this x here?
Yeah.
That's the area of one of these faces. It's just length times width.
Oh, okay.
Is that okay?
Yeah.
Imagine you folded this box flat. You'd have 4 of this rectangle, and they'd all be attached to a square at the bottom. It's called a net now in geometry, so it would look like this. And this box down here is x by x, so this rectangle is x by 4 over x squared.
Okay.
Okay?
Got it.
Let us find our first derivative. You know what? Pink hasn't gotten much love today. The surface area's derivative in terms of x is 2x minus 16 x to the negative 2 2x minus 16 over x squared. My goodness. So we're going to have to try to find critical values of this. That means we have to figure out places where it equals 0 and where it's undefined. Well, it's clearly undefined when x is 0, but that doesn't matter because you can't have x equals 0. If you had x equals 0, you wouldn't have anything to work with. So really, what we're going to have to figure out is where this thing equals 0. Did you like big brain your way to 2 and just saw it, or did you do more work? Okay, she just saw it. Big juicy brain. Instead of that, what I'm going to do is manipulate it using some algebra. Our choices either are to set it equal to 0 and then move this to the other side and cancel the fraction, or everybody's favorite, find a common denominator and create a single fraction. I'd say that the common denominator is x squared, wouldn't you? So if I multiply the top and bottom of this by x squared, I'll get that. Because it already had an x.
Yeah,
So x times x squared will give me that.
can't you just know that like 16 divided by 4 is,
Well, yeah, but that's only if you know x is 2.
okay, but you can't kind of just,
Big brain your way there? Sure.
If it's a bigger equation.
But if it's nastier, it might be hard to big brain our way there. Like, let's say it's quadratic and you'd have to factor it. You're better off just doing this. Because when are fractions equal to 0?
when a fraction is equal to 0,
When the top equals 0. So basically what we're trying to figure out is where does 2x to the third minus 16 equal 0? So add 16 to both sides, divide by 2. And then cube root both sides. So yeah, x is definitely 2. Time for our sign diagram. That is a single critical value on it. That had better be a minimum. Does it go on forever? No, I'm sure there's an upper limit to x. But we don't need it. And why would we not need it? Because this thing is technically a positive cubic. It only has a single minimum. So we don't need to figure out where the upper limit is or the lower limit is, because it's not going to be 0, right? We got put an x equals 2 on there, and then check a number between 0 and 2, like 1. That would make this top negative, the bottom positive. Yep, decreased down to 2. Just check a number after 2, like 3. 27 times 2 is 54, and 54 minus 16 is definitely positive. That tells me that my my surface area curve was doing this around the value x equals 2. Decreasing to increasing, which is definitely a minimum at x equals 2. The question asked us to find the most economical shape. So that means, what are the dimensions? Well, if you go back up here, That gives us a 2 by 2 base and a 4 over 4 or 1 height. So those dimensions are 2 by 2 by 1. Length, width, height. That's the most economical. Uses the least amount of surface area to create a volume of 4. That honestly is industrial engineering. Right? If you're a business owner, don't you want to figure out? Do you know there are there's a machine. Did you know there's a machine? I mean, I'm sure it's ridiculously expensive, but for Amazon and stuff like that, that scans packages and then it produces the perfect box for that stuff, price-wise. It goes, this is the best box that we could possibly ship that stuff in to minimize the cost of our cardboard. Now, does Amazon use that? I don't think so, because I've seen some ridiculous things, but I do know the box exists. I watched a video on it, or the machine exists. I watched a video on it. It was really cool. Anyway, you were trying to ask me a question. What was it?
How do you know that's the least surface area?
Because it's the minimum on that function.
Oh.
It's a cubic, so this cubic has this shape. It's a positive cubic. It has a single minimum. And would have looked like this. And we can only do things to the right of 0. Cool? Okay. Next. Is your next one this triangle drain one, or no, it's this one. Okay. Here we have a semicircle, and its diameter is 20. That tells us its radius is 10. I could do basic geometry. I promise I'm smart. That tells us our radius is 10. So there are infinitely many rectangles that could have been inscribed in this semicircle. What we want to do is find the shape of that rectangle that maximizes. Find the shape of the largest rectangle that can be inscribed. So I think what we're going for is maximizing area. I mean, how do you define largest? You know, because they're all trapped inside that shape. So I would say we need to maximize our area. Of the rectangle, obviously. Well, area of a rectangle is length times width, right? Anybody see anything that might be useful for me to draw? Ah, triangles. But specifically, right triangles. Well, you tell me. What is the length of this red line that I just drew? It's 10. That's the radius of the semicircle.
Oh, this makes my brain.
What? We're not. Well, we're not going to guess at a 30, 60, 90. I don't know. Okay. The way that I drew this picture, remember, well, I didn't draw this picture. The way they drew this picture and I stole it from them, it's not drawn to scale of any kind. All right. Well, Yeah, you have a question for me?
Wouldn't you know it's a 36 and 90 because isn't it 80, 180 feet?
Well, this is 90, but it doesn't guarantee that this is 30 and this is 60, because I could have drawn a really skinny rectangle. Okay. Do we know this length down here of this triangle? No. I tell you what, why don't we call it x? We don't know it, so let's just call it x. And obviously, I could call this y, right? And what I'm going to do is I would like for you guys to tell me how I can relate y to x. Yes, Julia?
So if you know that one's 20, wouldn't you remember that the bottom part is 10?
No, because it doesn't touch the side of the.
Oh,
It doesn't go all the way to the
okay,
edge.
got it. Yeah.
So how can I relate y to x? How can I write y in terms of x? The Pythagorean theorem. Because what we know is that x squared plus y squared equals 10 squared. Let's figure out what y is on its own. Y squared is 100 minus x squared. And then taking the square root of both sides, ignore the negative version because you're not going to have a negative side length of a triangle. That makes no sense. Y is the square root of 100 minus x squared, which is not 10 minus x. You can't do that. Okay? There. So why did I care to find this? Because, like Ethan said, no. Because if I know this x here, Ethan was right, I needed triangles. But if I know this x here, I know there's also an x here, right? Oh, look, now I know the length and the width of my rectangle. Area is length times width. And our length, if it doesn't matter which one is length is which one is width. It actually doesn't matter. I'm just going to define this as length, is 2x. And our width then would be this y value, which is the square root of 100 minus x squared. Can I not just write what? No, you can't just write 10 minus x. I just said that. 100 minus x squared is 10 minus x times 10 plus x. Since those two things are not the same thing, square root does not. If this was a multiplication dot, yeah, you could take the square root of both of those objects, but not when there's pluses and minuses in between that. Okay. Shake it off. All right. So, I'm wondering what would be the best way to handle this, because we know we're going to have to find its derivative in a second. I really don't want to mess with the chain rule, to be honest with you. By the way, I've never done this question before. So I don't want to do the chain rule. Would you mind if I manipulated it so that everything was underneath the square root bar so I could just use the chain rule? That's what I just said, chain rule. You meant to say let's just do product rule? You don't want to do that because then in a minute you're going to have to figure out where it's undefined and where it equals 0. That would suck, right? Yeah, that would bite, wouldn't it? So I'll tell you what we're going to do. Instead of saying it's 2x, why don't we say it's the square root of 4x squared? Because this will allow us to combine them into a single radical.
Did you also get the square root bar or 1/2 and the square root of x squared?
No, that would be the same thing as taking the square root of the 100 and the square root of the x squared. But what I could do is, like I said, I can combine these, and that would give me the square root of 400x squared minus 4x cubed. Yes, it would be to the fourth. This is like quality content for YouTube, folks. I'm telling you. Let's find our derivative. They're not monetized. I don't know. I'd be afraid to monetize them. I don't know if they could fire me for that. Technically, anything I produce for my classroom belongs to the school board. Doesn't matter that I created it. I do not have rights to it. Yeah, give them a cut. There you go. Shut up. Here's your cut. Sarasota County School Board. Let's find the derivative.
If you had 4 cents. 4 of your hard-earned cents. Yeah.
4 of my hard-earned cents. Let's bring that 1/2 down to the front. Don't touch the argument. Subtract. Now times the derivative of the inside. You okay? You gonna make it over there? Times the derivative of the inside. That's gonna be 800x minus 16x to the third. This question's fun. She says, I hate it. I think it's fun. $800x minus 16x to the third all over 2 square root of... Oh, calm down. It's not that bad. Oh, it's just... Anyway, critical values are going to be where the function is undefined and where the function equals 0, right? Well, we know that this thing equals 0 when the top equals 0 because it's a fraction. Could I technically manipulate and figure out where it's undefined as well? Yes. But I know I'm trying to maximize my area, so why bother? Why bother? All I need to do is figure out which x values will make the top equal 0, create a sign diagram around them, and I'm ready to rock and roll. Cool? So set the numerator equal to 0. And solve for x. Well, you factor, trust me. Factor. We're not going to divide by x. Okay, we're going to factor. We're going to factor out a 16x. Yes, 16 goes into 85 times, so it goes into 850 times. Huh? So where are our zeros? Clearly, x equals 0. And the other one is going to be where 50 equals x squared, which is plus or minus square root of 50, which is plus or minus, this is 25 times 2, so it's 5 root 2. Does negative 5 root 2 make sense? No, of course not. So really all we care about is positive 5 root 2. Yeah. We don't need to find where it's undefined because then that would mean that this shape simply doesn't exist. And clearly those numbers are going to happen when x is 10 and when x is 0. Because 10 would give you no rectangle and 0 would give you no rectangle. And since this number is between 0 and 10, we're in good shape. So we know, like I said, we know that this thing is limited by 0 and 10 because if it's 10 on each side, then you just have a straight line. You do not have a rectangle. So my sign diagram from 0 to 10. 5 root 2 is just a little bit bigger than 1/2. Actually, it's a lot. It's pretty significantly bigger. It's like 7 and change, I think. 6 and change. Whatever. 5 root 2. Guarantee that's going to be a maximum, but just in case. Sign diagram. Let's plug in 5 right here. Well, out there is positive, and 50 minus 25 is positive, so positive. Now we have to pick a number that's bigger than 5 root 2. Since I don't know the exact value of 5 root 2, I'm going to say plug in like 8 or 9. 9 is safe, so let's plug in 9. So, by the way, I know that 6 doesn't work because 50 minus 36 is still positive. So let's plug in, actually, so it's bigger than 7 because 50 minus 49 is still positive. So I'm going to go all the way to 9. Positive, and 50 minus 81 is definitely negative. So we know our shape was climbing and then falling. So your maximum area happens when x equals 5 root 2. And if x equals 5 root 2, then what does y equal? Well, no. You have to solve for it. Plug in 5 root 2 right here. So y equals the square root of 100 times 5 root 2, excuse me, minus, times 5 root, minus 5 root 2 squared, which is 50. It gives me 100 minus 50 underneath the radical, or the square root of 50, which is 5 root 2. How about that? So as it turns out, the area is maximized when this is a 45, 45, 90 triangle. Shock. Dirty little secret.
You knew that, didn't you?
Yes.
Oh.
Dirty little secret. Rectangles are maximized when they're squares. And since this one is inside a semicircle, it will be maximized when it's split into 2 squares. Which means 45, 45, 90 guarantees a maximum area. Yeah, well, look, that just comes with experience knowing that. Okay? And what time do we get out of here?
In 2 minutes.
In 2 minutos. Well, the good news is that the last example was just another maximizing the area kind of question. So it's not even anything different. So that's good.